GSM presents, from the U Garden restaurant near the campus of the University of Minnesota Twin Cities, the Geological Society of Minnesota is proud to present Miss Kate Clover and Digging Into the Stories of Sand. Kate Clover retired in 2016 after 26 years at the Science Museum of Minnesota. She served as a program manager and the geoscience educator. She developed interactive activities for exhibits and linked exhibit themes to cultural and natural resources, geology, flora and fauna, foods, and history. She also developed the Collector's Corner, a trading post where kids of all ages could bring in objects from nature, like rocks, shells, bones, sands, and insects, earn points for their knowledge and object, then use those points to get other objects. She also curated the sand collection. Kate considers herself a lifelong learner and loves doing deep dive research projects. Many of her projects involve sands, something she's been interested in since childhood. Kate loves looking at sands under the microscope, a vintage American optical stereo zoom scope, and figuring out what the grains are and what story the grains are telling about the local and regional geology, marine ecosystem, and native history and modern industrial history. Kate, a geologist and writer, co-authors and publishes the SPLENDID Sands calendar together with Leo Kenny, photographer and graphic designer, and Carol Hopper Brill, marine biologist and writer. From the calendar project's inception in 2008, their goal has been to illustrate the beauty of sands and to explain the science, history, and geography behind the samples. Kate also writes for and edits the Geological Society of Minnesota newsletter, as well as serving on the board. She is also assistant editor for the International Sand Collectors Society newsletter. Kate has a BS in Geology and Technical Writing from Michigan Tech and an MS in Science Education from UW River Falls. She also studied marine science through Clemson University. Digging into the stories of sand. Sands from around the world vary greatly in both their rock, mineral, and biogenic content. Other samples contain grains that record past industry and commerce. This talk will highlight the different locations with Leo Kenny's sand photographs. We'll talk history, geography, geology, marine biology, and identify grains. Locations include Madeline Island, Wisconsin, Wells Creek, Tennessee, Coos Bay on the Oregon coast, Haverstraw, New York on the Hudson River, plus a couple of other locations. Today's presentation is split into two sections, the main presentation and questions.
Anyway, thank you for inviting me tonight, and I look forward to talking to you about some sand. So, I titled this, Digging Into the Stories of Sand, and yes, I'm Kate Clover, and I also want to thank my photographer friend, Leo Kenny, who's out in Boston. He does a great job photographing sand. So, this talk, I'm just talking a little bit about me and collecting sands, and then we're going to fly around the world a little bit and look at sands from a few different locations. We're going to hit Madeline Island, Wells Creek in Tennessee, then we'll go to Iceland, and then we'll go to another island in the Galapagos. So again, Leo's the photographer, and he shoots pictures with his camera, with macro lenses, so not through the microscope, but he does a great job. And his lighting is excellent. That makes the pictures really nice. So my interest in sand kind of began in Muskegon, Michigan, where I grew up. And that shoreline there is just sand dunes and more sugar sand, as we called it. Mostly quartz. That picture's got some other mineral grains in it. But let's see here. Let's get my pointer going here. Okay, there's the little laser pointer. Okay, Muskegon is here, kind of right across from Milwaukee. That's where I grew up. And all up and down this shoreline is just beautiful white sugar sand beaches. And somebody was just talking to me about Indiana dunes and, you know, similar dunes here. But we lived about 5 miles inland, and you could dig a hole in the backyard, you'd still hit sand, you know. Great drainage, but my father was a gardener and he really didn't like that so much. So, and as a kid, we went up to Lake Superior and to Copper Harbor, and all of a sudden I was there and I'm going, wow, the sand is not white anymore, so what's going on? This is when I was a kid. And, you know, I looked around and then I saw there were some red rocks up there, so I kind of put two and two together and figured out that that sand probably came from that, from those rocks. I really had no idea where all that sand on Lake Michigan came from as a kid. You know, it was everywhere. It was just part of the shoreline. So, and we went up and down the shoreline as kids too, all the way up to this Mackinac Straits, and it was just the same white sand. And it was just kind of mind-boggling to me how extensive that sand really was. So my collection, I probably got about 3,500 samples, and that's a wall case, and it's got over 1,000 samples in it. And there should have been another little picture here showing the little 2-gram vials that I put my sand in, but I don't know why that is not showing up. So we're having a little problem about some of the photos not loading here, so I think that's what might be happening. We'll see.
Oh, they're there.
Oh, there they are. Okay. Okay. So they're really not that big. They're just a little, about 2 inches tall. So I have a microscope. It's an old American Optics microscope. I've had it for years, and it does a great job. So I can kind of sit there and pick up samples and pick out the good things, and it's always fun. So looking at sand is, for me, is kind of like research rapture, and it's kind of like forensic science. I never quite know what I'm going to look at when I look at a sand. You know, I pick it up off the beach, and you know, what you walk on, it's like, what is all that? But once you start looking at it, it's like, golly, you know, where is this place that I'm looking at first? And, you know, then I find a map, and then I dig into the geology, and, you know, sometimes I can look at the mineralogy and try to figure out what I am looking at. Sometimes it's pretty obvious, but sometimes it's like, I haven't a clue. Yeah. So I was digging into the mineralogy and going into the databases and figuring that out. Sometimes I find fossils. And, you know, sometimes I have equivalents down on the right side. That's a bryozoan that you're looking at there. But we also see similar fossil bryozoans. These are modern ones. So, but sometimes the sand kind of takes me into the history of an area. Sometimes into kind of industrial archaeology. And of course, you know, I always want to travel to some of these locations to see what it's really like. So, and then it's always curious, like, what am I walking on? When you go to the beach, do you ever wonder what's in all that sand and what makes it up? Why is some pink, some white, some black, some red? So, but anyway, I just have found it really interesting over the years to look at it. So we're going to look at some sands today. As I said, we're going to go to Madeline Island, we're going to go to Skarsvik, Iceland, Florian Island in the Galapagos, and to Wells Creek in Tennessee. So as you can see there, the sands are all very different. Some of those sands also have little scale bars on there too, so you can see the different sizes of the sand grains. So first we're going to go to the Apostle Islands in Lake Superior. How many people have been up to the Apostles in Madeline? Okay, it's a great location if you want to just go up and enjoy it, or need a little geology field trip there too. So the Apostles are on the part of the Bayfield Peninsula, and here's Duluth here, and this is the Keweenaw of Michigan too. So, you know, want to get a good northeaster wind, you know, it's going to come down here and really going to put some good waves along the shorelines too. So, the Apostle Islands are a national lakeshore, and that was established in 1970. Madeline Island, however, is not part of the park. There were just too many people living on the island in 1970, so they excluded that island. So you can see all the other islands here on the map. All this yellow represents the Bayfield group of Cambrian sandstones. And the little chart here on the right side kind of shows the different ones, but there are three different sandstones found in the Bayfield Peninsula. The Chiquamanon, which is the yellow, and the Devil's Island sandstone, and also the Orienta sandstone. And those are the green on the western side. And also to note while we're here is this little spit of sand right here too. So that is Sand Island. And so all that sandstone was a valuable sandstone to quarry way back when, and there were 24 companies that quarried that sandstone in the late 1800s, and that was shipped all over the Midwest. And the Washburn State Bank in Washburn, Wisconsin is made of that beautiful red sandstone. And the sandstone is really hard, so it does not erode really well. And back in the early 1900s, late 1800s, you know, building buildings out of stone meant they were not going to burn if there was a fire. So, valuable buildings material. So a little bit of history here. Before the Europeans, Madeline was home to the Lake Superior band of the Ojibwe, and they still consider the island their spiritual home, and their reservation is up on the northeast point there. So, and this is La Pointe here. That's the main town in on the island, and here is Bayfield. So if you go to the island, you take the ferry from Bayfields to La Pointe. So those are kind of the two main towns there. So La Pointe was the site of a French trading post at one point in time, and you can see that this is kind of a protected area here. So that was a good area to have a fort. So in the late 1700s, you know, the fur traders came, and they also established a fort there too. And then the loggers came, and you know, they stripped the land of all the white pines. And then, of course, the quarrymen came too, and they came for the sandstone. That was, again, late 1800s, early 1900s. So once bricks came in, big sandstone kind of lost in favor with builders. And Madeline Island is about 14 miles long and about 3 miles wide. So we're going to look at two different sands from Madeline here. And we have one sand from Big Bay, and we have another sand from Grants Point. And here are the two sands. You can notice the different scale, or the different grain size on these pictures too. So most of the island is underlaid by sandstone, and you see that on the shoreline. Some of these pictures are not coming through here, so I'm sorry. There was another picture of a shoreline there. So, but a lot of the shoreline has that sandstone there, and it dates to about 1.1 billion years old. And you do see ripple marks in there, and that kind of indicates it was laid down in a lake environment. So, all right. The other sand we're going to look at here is from the town park, Big Bay Town Park, and that is right up here. This is Big Bay here. And this sand is, you know, the equivalent of Lake Michigan sand that I grew up in. It's white, it's very fine grained, and it's very shallow in this bay. If you go up, this is a great area to go swimming, take the kids. It's a pretty little place. So the sand here this is looking rather red in this picture, but it really isn't that red. So here's Grants Point. At the southwestern point. It's kind of near the old fort there too. And here's Big Bay here too. So those are the two locations that we're going to look at. This top picture kind of shows you how much sediment is in the water. That is just sediments in the water from the grains, small grains, fine grains being blown offshore. If you look at the big map here, you can just imagine all the big waves coming in off Lake Superior, especially with a good northeasterly wind. So hitting this point and then just putting all that fine sediment into the water. So I camped around the point from around the point from Grants Point, and we kayaked around here, and you can actually see all the sandstone, or excuse me, all the glacial deposits that were deposited by the glaciers, and the sand all comes from the glacial deposits. And it erodes from the big storms that come there. You know, back when I grew up, there used to be ice on Lake Superior in the winter, and of course the ice protected the shoreline from the big waves and the winds in the winter. But today we have higher winds and milder winters, so we have a whole lot more erosion on these shorelines. But a lot of the cliffs look like this. So again, we're missing some pictures here too. So
try reloading, go back or continue to work on this.
oh, okay. Well, all right. I said okay. Pleistocene deposits. Oh, they all came from the Canadian Shield. All right. So at Grants Point, we get we have coarse, very coarse sand here, and all the fine grains are all kind of winnowed away, blown away by the wave action. So in here you can see all the different grains, and what we do see here is some very rounded quartz. We see some feldspars with good 90-degree corners here. Got some granites here. And probably another kind of a yellowy feldspar down here too. But this is a very coarse sand. So if you look at it, those grains, it's individual grains. You've got some rhyolite up here. This I think is anorthosite. It's kind of grayish looking, green-gray. And of course that would have come from like Carlton Peak. And red rhyolite, feldspars. 90-degree corners here. I think we got some agates here. This looks like agate to me. Likewise, that one. And this grain looks to me like it could be a garnet based on the shape of the grain. So Madeline Island we're looking at sand from two different locations, and we just noticing how coarse it is from Grants Point and fine grain from the Big Bay Town Park. And you also get a heavy minerals some sand on the island there too. So let's see, let's try that one again. Okay. I always love looking at these kind of deposits with heavy mineral sands. They can be very pretty, and it's probably magnetite and ilmenite, along with the quartz. And these kind of deposits are mostly created when you've got some really heavy winds, oftentimes in the winter, because in the winter the higher waves will take the less dense quartz and move that offshore, and that leaves the heavier mineral grains onshore. And then as those conditions change, you get these different deposits of different colored sands. So here's that heavy mineral sand. Magnetite, ilmenite, nice pink and red garnets, and quartz and feldspar, of course, too. So anyway, it's a beautiful island and great destination for a geology field trip if you want to go up there and check it out. So, and beautiful beaches, kind of a funky little town, La Pointe. So, all right. We're going to leave Lake Superior, and we're going to go to Tennessee now. All right? So, here's a little map of Tennessee, and on the far right you can see Nashville, and this sample is from near Cumberland City, and Cumberland City is up here to farther west. But it's about 70 miles from Nashville. So, but when I looked at this sample, it's like, whoa, what do we got here? So, there's some blue slag, and there's a fossil, and so it's like, it just makes me kind of ask, well, what's going on here? So, what did they mine? When did they mine it? Where did that fossil come from? So, again, kind of just, I never quite know where my research is going to take. I throw one of these samples under the microscope and go, whoa. Something to figure out here. So, So here's this blue slag. So, that indicates that there was some smelting operation going on. But I go like, okay, what was smelted and when was it smelted? What was mined? And then there's that fossil crinoid in there. So, all right, what does that tell you about that region at one point in time? So there must have been some ocean. So you start looking at a map, a geology map of Tennessee, and you see this big blue area, blue and pink area in the middle. Well, check out the key down here, and you learn that was the Devonian Sea about 320 million years ago. So that kind of explains why we are seeing fossils in here. And I only found the one crinoid in the sample. I'm sure there are more if we had a bigger sample. So anyway, and then the iron mines, okay? There were some in Knoxville, but we are looking over here at Wells Creek for this sample here too. So why are we finding iron mines over here in Wells Creek? So that was kind of one of the questions there. But iron was mined there from the early to mid 1800s. All right, this is a nice picture that Leo did of the different grains there. So you can see some of the slag is green, some is purple, and some is blue, and we've got some crinoids there too. So, and the blue slag is kind of pitted, and those are gas bubbles that got into the sand as the slag was cooling. So, it's a picture of one of the smelters in Cumberland area, and they were fueled with charcoal. And at first they went into the woods and got the wood and made the charcoal from that, and they got some limestone from another location nearby, and mixing those together, they reduced the ore, and they got molten metal, and then the waste material, and that waste material was the slag. So the whole process, subjected the iron and the slag and all to high temperatures so that the iron separated from the slag. So and then those impurities all kind of float to the top of the big pots, and they pour that off, and that's what you have as slag. So around the area, there's some really odd-looking rocks. And when work started on the railroad in 1854, the engineers and the surveyors said something's kind of haywire here. This is really odd rock. So they brought in some geologists, and they actually mapped it briefly, and they kind of got this map, and this map was included in the 1869 geological map of Tennessee, but they had no idea what this structure was. So a NASA scientist in 1960 went over there, and they wanted to see if lunar craters were related to what we were finding on Earth. And so they looked at this crater, and if you look at this picture, maybe you can see some really zigzaggy, fractured Earth here, and you can see more over here. And it's on the land is all fractured. Remember, this was an old lake bed, so this really stands out as being different from everything else around it. So they confirmed it was a meteor impact site, and that occurred between 100 and 300 million years ago. And a diameter here is about 12 kilometers across. And I love all maps, so I dug a little deeper, and here's another geological map of the area. And this is over here on the right side is kind of a blow up over here, but you can see how all the topographic lines here, and also noting there are all these little mining cross picks here along the edge, and those signify all the different mines that were along the crater walls. So some say Fe, that just probably straight iron, and here's one that says FES, so it must have been a sulfide area down here. So, but all the way around this crater were all these mines where they were mining the ore. So also found in the crater are these little shatter cones, and these form from the high pressure of the impact. And you can see the size of this one in somebody's hand. So an interesting sand, and got to learn about slag and iron mining in Tennessee, and a little bit more about that inland sea that covered the region. a long time ago. And then again, this is a sample, an anthropogenic sample. It shows a little bit of where command has been. So. And also it's an impact site, which is pretty cool to see. All right. Now, let's see, I think the last slide said we were going to go to Iceland from Tennessee. So hop on that Icelandic Airlines airplane, and we're going to land in Reykjavik. And Reykjavik is about 6 degrees south of the Arctic Circle up here. So, and I was there in the summer of 2022 with the Institute for Lake Superior Geology, and there were like 6 of us from GSM. And, you know, we had some good weather and we had some winter weather in July. So it was a great trip. One of the places we went, so this was a sample I collected up in the Highlands at this Fljótsdalur Valley. And that's way here in the inland. And I love picking the Icelandic words apart. And Orr means place, Dal is a valley, and the Fljóts means large river. So it's a valley with a large river. So, and the sand we got up there was black, and there was some red in it, and there was a little bit of yellow. And yeah, yellow was definitely olivine. So that was pretty cool. And to get there, let's see if I can get the rest of the slide here. Okay, so we stayed in Eidalstaðir, I'm sure I'm mispronouncing that, and our destination for the night was to go to Dreki. That's where we're going to spend the night. So that was 100 kilometers, and it just took us 4 hours to get there. And the ring road is road number 1, and that goes around the island, but once you get on these F roads, which are that go into the interior, they are only seasonal roads. And so we were on the 910 for a lot of miles. So coming here and going here, down and back up, and you know, finally we got to Dreki. So it was a wonderful trip. So these are the roads, these are the F roads in Iceland. Yes, there are road signs, they help you navigate. Sometimes they look more like a road than other times. Many of the signs are so windblown and so eroded from the blowing sand that these were fresh signs. But here we were going, Aska was near Dreki, and that is still 85 kilometers, so long way to go. Very bumpy road. Oh, all right, and part of driving the F roads was driving through rivers. So, and that was pretty cool. All our drivers were exploration geologists, very comfortable driving four-wheel drive vehicles through rivers and whatnot, and all over very rough terrain. But all our vehicles had GPS little jobs in them, and it worked. It was pretty cool to see where we were actually going. So there's another couple pictures of the landscape there, and probably the left picture on the left is where I collected that sample. And here's another picture of the road. You can see this row of rocks here. Those are just the edge of the road, so you know, stay there. And they really want you to stay on the roads and not destroy the landscape. So by driving over it, you get fined if you do, if they can figure out who you are. But windswept terrain, you know, and if you do go to Iceland, you always want to make sure that you buy the car insurance, because if you get up here and your car gets sandblasted, the car rental company will charge you for a new paint job. So a couple more pictures of the landscape here, and a lot of times the picture on the wind is wild up there. You know, nothing unusual about a 40-mile-an-hour wind all the time. But the winds blow all the fine grains away and kind of leave this desert pavement you see there. Just coarse stuff. So the sample that we looked at from the Eastern Highlands, which was in Vatnajökull National Park, you know, contained a lot of this basaltic magma, lava rock. And of course, basalt contains iron and magnesium, so you've got these red grains here too. And if it was raining or snowing when that magma was erupting, the iron oxidized, and then you got some red grains. So, and if you look here on the right, you can see how well-rounded these grains really are from just being sandblasted and wind-blown. So this is what happens in the high desert with all the grains too. So we've also got some olivine here, some of the iron rusted basalt, and a couple feldspars as well. So after, that 100 kilometers, we finally got to Drecke. And these are the huts we stayed in. And altogether, those huts sleep about 50 people. And it's cozy. It's really cozy. There was a communal kitchen where everybody kind of cooked and we ate. These are all Minnesota Geological Society people here. And upstairs in, I think, this A-frame, this is where our group slept. There were 16 of us on the trip. This room here slept 12. And this little alcove, this is where we 4 females got to put our sleeping bags down. It was cozy. So bathrooms were downstairs, so it was, we had to truck down there and whatnot. These tents back here were part of NASA. They go up there and do a bunch of experimenting and do some practice stuff for lunar work too. So those tents were all NASA tents. You never saw them. And this is an outhouse. So, I don't know why they do triangular ones, but they put these giant rocks on the sides of them so they don't blow away. And they do, We're going to Drecke because we wanted to go to the Aska volcano. But, once we drove there, the wind was blowing about 40 miles an hour, and it was cold and snowy, and we didn't have the right shoes to walk on the snow. So we turned around and went on to our next destination. So anyway, it was a great trip. If you have an opportunity to go, do it. So, and another sand from Iceland is from the Vik beach. Lots of people go here, but of course this is wave washed sand, and those grains are very well polished from the wave action there too. So, and I stayed a couple extra days beyond the trip, beyond the group trip, and I went out to the Snaefellsnes Peninsula here on the western coastline here too. And Snaefellsnes means snow, fells is mountain, and then Ness is a peninsula, so it was a snow mountain peninsula here. It's a big volcano up here that is snow covered. And when I went out there, I just played tourist. July, August, I was there. So, and one of my things I wanted to do at the Snaefellsnes Peninsula out here was go to this Skarskovik beach, and it was advertised as a yellow sand beach. I'm going, well, I gotta go find out what yellow sand really means on Iceland, where everything is all basalt. So, it was a nice drive out there, beautiful day, and the beach itself did not kind of look very yellow to me, but if you look at it up close next to this kelp, there was some yellow in here. So, and then if you look at it under the microscope, you certainly got more of that caramel colored yellow there. And all that yellow, those are barnacles. So, and this part of the peninsula is on some of the oldest land on Iceland. You probably all know that there is volcanic activity happening right now, kind of near Reykjavik in the Reykjanes Peninsula. But the oldest rocks on the island are on the far west coast and on the far east coast. And so this is an area with a little tiny cove where the barnacles have kind of gotten established. And you don't see too many barnacles or too many shells elsewhere around beaches. So you do need older rocks where they get established and whatnot. But all these yellow and caramel colored, those are all barnacle fragments. And then of course blue mussels. They've gotten established there too. And here's a sea urchin spine. So pictured on the right is a barnacle, and the barnacles have got like 6 plates in their base plates, and then they have the operculum, which is kind of their trap door right at the top, and there are 4 more plates here, so it's kind of difficult to identify these sometimes. But based on the color of that sand, all the yellow was the barnacle. So, yep, there's the sand again. So we went to Iceland and we saw 3 different sands here. One was all windblown and rounded because of the wind and the abrasion caused there. And one was the an ocean sand that was rounded by the wind and waves. And then we had a sand full of barnacles and mussels. And that was in a little protected beach. So nice to see something other than black sand from Iceland. Lots of people have brought me sand back from Iceland and it's always black. Go for the fun stuff. All right, now we're going to go from 6 degrees south of the equator, and we're going to go to 1 degree south of the, 6 degrees south of the Arctic Circle, and we're going to go to 1 degree south of the equator. And you can do it, you can do it. Okay, we're going to go to Floriana in the Galapagos. And that's part of Ecuador. And there is some sand on the beach there too, amongst the rocks. So Floriana, yes, okay. You find a sand with olivine in it, and that just immediately says, okay, this is a volcanic island. It has volcanic origins here. So, and it's amazing to look at this sand and see how well-rounded those grains really are. Of course, that happens, you know, when you're rock polisher at home, and it also happens out on the shores where there's lots of intense wave action, polishing the grains. So we've got, you know, different colors of these nicely polished grains. They kind of look, colors are bad here, but they can be kind of green to yellow to black to red. So again, all right, here's Ecuador, and it is 1,000 kilometers off the coast and about 620 miles. And in 1976, it was the Galapagos were recognized as a UNESCO heritage site. So a little bit of history there. So here is Floriana here, and this area is another volcanically active region on Earth. And so this little island, La Cumbra, Ferdinina, was erupting this spring. So this is where the active volcanoes are on the Galapagos. And here's Floriana. It is one of the oldest islands in the archipelago. So this, the Galapagos are on the Natchez Plate, and that is moving kind of towards the southwest. Here's the Galapagos here. This plate is moving kind of to the southeast, and the Cocos Plate is kind of moving to the northeast. So you've kind of got some twisting going on, and that's kind of making the oldest islands to the southeast and the youngest to the west. So there's a map of Floriana, and Punta Cormorant was up here on the north coast, and this kind of just, to me, it looks like a nice big shield volcano, nice, something about it. There's a big, the summit crater was up here, but there was another crater here. And it's called Cormorant, but there are no cormorants there. There are some flamingos that do live in a wetland lagoon, kind of be inland a little bit, but there are no cormorants. So, and from that volcanic rock, we've got a lot of olivine eroding, and then you've got some of the tuff coming out too when magma encounters the water when it's erupting. So, okay, so it's a nice close-up shot of a bunch of those grains. Notice the similarity in shape of a lot of these here. So most of us know that olivine can be kind of olive green in color, but it comes in many different colors, and we find a lot of it in the Galapagos. So, and then we find some of these tuffs here too, and some heavy minerals as well. So, but if you notice the red grain here, and this kind of yellowy green one, and this kind of clear colored one, similar shapes. And even if you look at the one on the lower left side here, you can just see this is a fragment of some, like an end here. So similar mineral shape. And first, if these were crystals when they were in the rock and eroded out, they're going to maintain their original crystal shape. But you just have to imagine a lot of eroding in the time, over time. So when we visited Jeff Thole and McAllister this spring for the fossil show, afterwards I got to go with him into the SEM, and he put a few of these grains under the SEM, and it was pretty cool to see. This was a grain he examined, and here's the spectrum he got there. Hang on, let's see. And that did show that it was olivine. And olivine is a manganese iron silicate, and it changed the percentages of manganese and iron, and you get different colors. So, but that one really showed up as olivine. And another grain was idigite, and that is an altered olivine where the iron is oxidized and it turns red. So I've seen this idigite from the Galapagos and also from northern Canada, northern Alaska area. So, but it's a beautiful red color, and you can see there's more iron in the spectrum down here too. And there was this bright green grain in there, and we got to zap that one under the SEM, and that was identified as a clinopyroxene. So, and you've got a lot of little unusual minerals down here, and Jeff is remarkable with just looking at the scan and he says, it's clinopyroxene, or it's idigite, and when he talks to us next year for his lab, you're going to see how knowledgeable he is with mineralogy, but it's pretty amazing. But I feel very fortunate to have spent a little bit of time with him looking at some of these grains. So, and olivine, as I said, it's magnesium iron silicate, and you change the percentages of iron and magnesium, and you get all different variations of olivine. Fosterite is kind of the yellow-green that we're familiar with. Phaolite is black to brown, and idigite is the red. So, okay, we've looked at these different sands today. We've been to Madeline Island, we've been to Iceland, we've been to Tennessee, and we've been to the Galapagos. So that's it. That's what I have for you today, and I hope you enjoyed those little stories about some sands. So, and I hope when you get to the beach next time, you kind of wonder what you're walking on. So, anyway. I was on Puerto Rico a couple weeks ago, and this is a sand I picked up there. It's like, whoa, that's pretty cool. So, yeah.
What is it?
Well, this is a part of a chitin plate right there. There are lots of sea urchin spines, but there's pink, and there's, lots of different ones. Some forams are in there. I haven't spent a whole lot of time, but it was kind of fun to find a chitin plate in sand. So. And this other sand did not get the location on it. Hang on, let's see if I get that one. Oh, that one is from Oregon. Okay. This one was sent to us by another friend recently. And this is from the Oregon coast. And it got some great minerals in some of the sands you find out there. They erode from the Klamath Mountains on the Oregon-California border. So, and a lot of the black is there is magnetite and ilmenite and probably some chromite too. So anyway, so any questions from you guys? Yes, Glenn.
It's my understanding that a lot of nations are now sensitized to the pain of people walking with the sand, and I'm wondering how you navigate that.
Glenn's question was, it's sometimes it's difficult to leave a country with a bag of sand in your suitcase, and there are some countries that are very sensitive to people leaving with natural resources. Italy is one. They say you shouldn't take it from Hawaii, but Hawaii. Some places they care, sometimes they don't care, but we, Leo and I, trade with people from all over the world. And so that's one way of getting around. And if you mail your sands home, you don't have to go through customs either. So,
Yes.
You use the word sand.
I take this as an example. The one on the left is obviously organic origin. We call that safe.
Well,
And I'm trying to differentiate between, when we say sand, it's a complex system, and some of it's biological, and some of it's non-biological. And how do you make that differentiation?
well, there's mineral sands, or lithic sands, and then there's biogenic sands. So what we have here from Puerto Rico is a biogenic sand. And of course, sand is also a grain size. And sometimes your biogenic sands are really, really fine grains, and sometimes they're really chunky and coarse. So, but you know, if you really get to it, but I don't like the clay-sized sediments because they're too tiny to even look at. So I really prefer stuff that is, you know, I can see and feel in my fingers. Yes.
And a follow-up to that, because with the organic, biologic, you can see an origin, and you can imagine the wave action breaking it down to that size. But then go to the non-organic side. It's hard to imagine, how could you back up from a grain of sand, the process that gets that thing from its source form down to the size that it is, that we call sand. It's hard to imagine that process.
You're right. It's very hard to imagine the process going from rock,
Just barely.
you know, as big as your fist, or a mountain, to a grain of
I
sand.
have to.
You know, it didn't happen overnight. You know, I think about all that Lake Michigan sand that I grew up with. That's an incredible amount of sand. And you know, today I can understand that there were giant mountains in Canada, the Laurentian Mountains, and they were granite, and you know, over time they broke down, and maybe they turned into sandstone at some point in time and were cemented together, and then that sandstone was eroded again. So multiple rock cycles going from rock to sand. With biogenic sand, you don't get that so much, but with lithic sands, of course, you do. So, to answer your question, yeah. I sometimes like, where in the hell did this sand really originate? Yes.
There's a famous white beach near Tampa.
The white sand at St. Pete's, is that on the Gulf or is that on the Atlantic? It's on the Gulf, okay. Good question. Where did the sand all come from on the Gulf? You know, that's the Appalachian Mountains eroding over millions of years. And rivers eventually got to the Gulf. And wave action made it really, really tiny, but that originated in the Appalachians. And that's also what you find out along the Atlantic coast as well. So, yes.
Well, to follow up on that, besides in Sarasota, Florida, and that's extremely light, extremely soft sand, in the sense that normally when you walk on sand, you kind of, oh, it's ouch, ouch, that kind of thing, and no, it's like, it's so soft. And I don't understand why the whole coast is sand, and yet certain places are so much softer than others.
It's probably grain size. And a lot of the Gulf Coast is also a lot of carbonate sand. It's not silica sand, it's carbonate sand. So that just sticks to your body too.
And Key West, I thought that.
Key West, you know, the Keys are coral sand, and also you've heard of the parrotfish, and you know, they eat the coral and then they poop it out, and that turns into sand as well. So that's breaking things down. Yes.
What are the grains like that make that singing sand up north?
Singing sands, what makes those? That's all grain size and grain shape as well. There's just a particular size and shape that you step on it, it makes noise. But you see it on Lake Superior and probably other places. I'm just drawing a blank where else we've seen singing. Oh, there's some on Oregon. Yeah. Mary Ellen?
When you're looking at these different samples, how much are you getting any plastics or obvious plastics mixed in yet, or has it not been enough time to really come down in grain size yet?
Oh, there's plastic. There's plastic. I was going to show another bunch of pictures here, but they weren't, they weren't loading here very well. So let's see if I can show you some plastics and sand. All right, not that one. Either.
That I could use to help.
All right, that's from Downey Beach, Florida. Another Downey Beach, Florida. Oh, maybe that's it. No, that's. There it is. Okay, that's all microplastic, or maybe a little bit bigger than microplastics in sand. Oh, this thing is advancing by itself. That's what's going on here. So a lot of the little beads here, little circles, those are just little microplastic beads. But you find all sorts of junk in sand that it's plastic. And you can see the scale bar on the lower left side. Some of these are a little bit bigger than grains of sand, but nonetheless they went together into this picture. So yes.
I have a feeling we're on top of the St. Peter sandstone.
We probably are on top of the St. Peter right here.
So can we have a word about it?
Or is it limestone?
Well,
One of each, some of each, Randy? St. Peter or?
We're sitting on a plateau.
This is the Platteville here, okay.
you could get your hands scratching it off, so it's not as hard as hard sandstone.
The St. Peter sandstone is not very well cemented together and it breaks down pretty easily.
Do you have any samples of the St. Peter?
Yes, I have. Nothing that I could probably dig up right now, but some of the St. Peter is very, very white, and some of it is kind of iron stained. And that's what Henry Ford mined to make window glass.
Okay. So is it mostly quartz, silicon?
Yes, it's very pure quartz sand. St. Peter was old dunes. Dunes, I think also lake bed. Randy, want to comment on that? St. Peter, what's this?
Still controversial.
It's still controversial.
The sandstone that we did when we went on that trip to Sandstone, Minnesota, did you get any of that to have a copy of pictures of this?
That would be a red sandstone from Sandstone. I don't have any of that, but I've seen it. But, you know, that's iron staining, which gives it that red color.
Yeah, this is the Hinkley, which correlates with the Schwalingen, I think, sandstone.
Okay. Yeah, the orange color, the red color on sands is kind of mind-boggling, you know. It's iron precipitating out of the atmosphere and coating all those sand grains. There was some time period in geologic time when there was a lot of iron in the atmosphere. This is my understanding. So.
Yeah, Mr. Rex, well, I've read articles in online, so they must be true, of course, regarding a worldwide shortage of sand. Can you offer any illumination on that?
A shortage of sand worldwide. Okay, the primary ingredient in concrete is sand. Okay, and to make sand, scientists or the concrete scientists really are looking for a particular, not really rounded sand. They want something kind of angular. So they're kind of particular about the sand they mix with good concrete. But concrete is the most common man-made product on Earth, on the planet. So everybody's always looking for more aggregate, more sand to mix with and put in their mix. And yes, people are mining sand, taking it from the rivers, taking it from the beaches, and of course that's causing more erosion and more problems along the way. So yes, there is a sand shortage.
Also fracking.
Oh, fracking, yeah. Mm-hmm. Yeah.
Kate, can you say anything about the frac sands?
Frac sand?
Yeah.
Frac sand is, the grains are all uniform in size and shape. And they use that to inject that into the wells and to break up whatever's underground so they can extract the oil. But all that frac sand is always pretty pure quartz, and it's uniform size and shape.
And there was a lot that was coming out of Wisconsin and Minnesota. So that, but which sand was it?
That, a lot of them, I think, was the St. Peter.
No.
No? The Jordan?
Jordan.
The Jordan,
Yeah,
okay.
St. Peter was not good enough.
No, St. Peter was not good. So there's, yeah. But you know, there's fracking going on all over, so there's a lot of different sands that are mined for that purpose.
Yeah, on the frac sands, they found now that they don't need to have as specific type. They can use a little bit different variations too, so that the Wisconsin sands that they were taking is not as necessary as they can get some local stuff. Shipping a boxcar load of or a grain car load of sand across country is very expensive for very little gain. So you want to do it as local as you can.
Okay, any other questions?
I actually learned about northern sand so I'm going to ask a question that other people might know, but I just found out that there's another kind of sand, which is the carbonate. I'm used to the one that's silicate that you can make glass out of. Can you explain a little bit about the carbonate sand? What is the origin of that? Or
That's all from marine organisms.
and but you said the other one.
Was rocky sand.
No, you had the one with shells.
Biogenic.
Biogenic, and the other one is
Lithic.
They both sound like they're.
Biogenic is biological organism. Lithic is from rocks. Originally from rocks.
And this other one, the carbonate, is from the biogenic.
Yes.
Got it.
No. Good question. Thank you. Way in the back.
You had said that you don't mess with clay much, it's too small. What about silt?
Silt's even smaller than clay. You know, it's just, you look at it under the microscope and you can't really see anything. Now with a microscope anyway, but I'm sure there are other people that, you know, appreciate clays. You know, if you're making ceramics, you want clay. So, but you go down to Iowa and you get some good clay down there, but you can also find lots of fossils in that, so that's kind of fun. Steve knows about that. Oh, what about silica? Silica is quartz. I'm not sure where that question is coming from. Oh, over here. Okay, silica sand is all quartz. Predominantly. You know, there might be some impurities in there that are your feldspars and some heavy minerals too, but silica sand is quartz.
Remember the action of these sands, as the waves wash over, feldspar will break up into fragments, and
As sands are formed, they get worked over very, very heavily. Feldspar will break up into smaller and smaller fragments. Quartz can only break down so far before it stops being broken down. You can knock all the corners off so you get very rounded, but the physics of it all, you can't get. It's like breaking a pencil in half, then you try to break it again, and you try to break it again. At some point, you just can't break it down any further. The same thing goes here with these quartz grains. So there's kind of a lower limit to how small they can get.
That's right. You still see feldspar grains, you know, I pick them out based on their shape, their cleavage. All right, anything else? Oh,
Hi, Kate, is there a limit to how big your sand collection will get? Will you run out of room in your apartment?
Well, I have kind of stopped collecting everyday sands. I will take special sands, but my friend Leo will take anything and everything. And, you know, I ship it to him. He puts it under the microscope, he puts it under his camera, shoots some really nice pictures, and today I am happy with some really nice pictures. Pixels are free. So, but I'm always interested in looking for another sand, but I never know what I'm walking on. So, and it just teaches me so much about the local geology, geography, and dig a little deeper, history, and whatever else. So, yes, one more.
Are there any other major things that sand is used for other than concrete and glass?
What else is sand used for other than concrete and glass?
Anything major, just questions.
Sandblasting. You have sandpaper. Oh, sand castles. Road sand. Beaches. Sand traps. Oh. And sometimes in ashtrays you have sand too. Of course, ashtrays, you don't see as many of those anymore. What else? Other uses for sand? Good question. Thank you so much, everybody. It was kind of fun talking to you.
Thank you all. We'll see you next year.